Okay, just like in the previous problems, our focus is going to be on the shear force and bending moment diagram. So I'm just going to give you the reactions. But again, I don't think it'll be too hard for you to figure out that you have P over 2 and P over 2. All right, let's start with the shear diagram. What kind of shear is this here? Positive or negative shear? Positive. Oh, finally somebody wants to play along. Okay. What about this side? Positive or negative shear?
Negative.
Negative. Excellent. Don't forget our sign convention for shear looks like this for positive. So obviously this on the right-hand side, negative. Okay, that's a good place to start. So now we'll apply our relationships that we've been using the whole time. The change in shear is the area under the load curve, right? And what is the load curve? Between 0 and L over 2. What's the loading? 0. So there is no change. So that means if I start at P over 2, I should end up at P over 2. And of course the slope of our shear diagram is equal to the load. What's the loading here? 0. So that means you have a 0 slope. 0 slope is a horizontal line. Now we've talked before about when you go from the left side, pass under a concentrated load to the right side, how does the shear change? In that case, the change in shear is directly equal to the load. Now that load is positive or negative? Negative. So that means we'll hit this point and we'll subtract P. So P over 2 minus P gives us minus P over 2. And now we proceed to the next section. In this section, the change in shear is equal to the area in the load curve, and that is no change, 0. So negative P over 2, negative P over 2. Yes, we did not need Siri to tell us how to get there. We found our own way. What is the... Wish Siri could do your test for you. Siri, do my exam for me, please.
That wouldn't be obvious.
What about the slope? Well, the slope's equal to the load, and the load is 0, 0 slope, horizontal line. So there's your shear diagram. All right, let's try moment. Was that a question? I'm sorry. You don't have to. Because actually, what is the shear right here in the middle? Unknown. Just to the left, it's positive P over 2. Just to the right, it's negative P over 2. And that happens almost instantaneously. And as structural engineers, what do we care about? The maximum. So what's the maximum shear in this structure? P over 2. It doesn't really matter whether it's positive or negative. Okay, so what's the moment? What's the moment at a pin connection? On the edge, right there, on the external connection. 0. What's the moment here? 0. Oh, perfect diagram. We're done. No, there's some variation in the middle. Unfortunately for you. So the change in moment is the area under the shear diagram. So let's apply that. So this is a nice area I can deal with. So what is the area under the shear diagram? It looks like a rectangle. So it would just be P over 2 times L over 2, which is PL over 4. And that's positive area, so we should go up to PL over 4. What's the slope of this line? Well, according to our relationship, the slope of the moment diagram is equal to the shear. And what's our shear value everywhere in that section? Constant, P over 2, and positive. Constant slope of P over 2. Now, from L over 2 to L, what's the change in moment? Well, it's the area under the shear curve from L over 2 to L, which is what? That's a negative area. It's a rectangle. Base L over 2 times height minus P over 2 gives me negative PL over 4. So that brings me back to 0. Cool. Slope is equal to the shear. The shear throughout the region is constant, and it's negative. So here's my constant negative slope. So I would have negative P over 2. And there's my moment diagram. So what's the maximum moment? Where does it occur? PL over 4, and occurs in the middle of the beam. All right, let's do this one. Uniform distributed. Take the total load of the structure, W naught L, and it should be divided equally. So I should get W naught L over 2 on this side, and W naught L over 2 on that side. Again, you can check that. So what is the shear on the left side to get started? Positive, and has a value of W naught L over 2. What's the shear on the right-hand side?
Negative.
What's its value?
Negative W naught L.
Wow, you guys sound like you've done this before.
I'm gonna hold this.
It's a
What?
picture.
Huh?
I said he likes it because it's a picture.
These colors.
What's colorful, huh? Okay, so what's the change in shear is the area under the load curve. What's the area under our load curve? Yeah, remember this is negative, right? So it's really negative W naught L. So if I start at positive W naught L over 2 and subtract, I get it. Cool. What's the shape of the curve in between? Well, according to this, the slope of the shear diagram is equal to the load, and the load is constant and negative. So if I draw this to scale, which I probably won't be able to do, it's close enough. You can see that I'm going to get 0 shear right here in the middle. Now, how do I know that? Well, let's investigate our slope. Remember, for every 1 you drop W naught. So if I go L over 2, I should drop half that. No, wait, I did that wrong. Well, that's right. I started out at W L over 2, and I go this distance. I'll drop that much. I'll get to 0, half of it. Now that's pretty cool. And this will be important later. And you see I already had the dotted line in there. I knew that was coming. Let's do the moment now. So what's the moment on the left side starting at the hinge? 0. Do we know the moment at the right side at the roller? 0. All right, here we go. The change in moment is the area under the shear diagram. So let's look at this first half. What's the area under this part of the shear diagram? It looks like a positive area. So it's going to be 1/2 base times height. 1/2 base times height is W naught L squared over 8. Well, you got a half, and a half, and a half.
Oh, okay.
L over 2, L over 2, and of course it's half the area because it's a triangle. So you get half times a half times a half. That's cool. What's the shape of the curve? Well, according to this, the slope of the moment diagram is the shear. What's the value of the shear when we start? Positive, negative, 0. Positive. So it's going to start off with a positive slope. In fact, if we labeled it, it would be minus W naught, W naught L over 2. and it's going to change to 0. So now I'll just connect those as best I can. Now, over the second half, from L over 2 to L, the change in moment is the area of that part of the shear diagram. And what is this area of the shear diagram? It's a negative area, and it's negative W L squared over 8. So that brings me back to 0. And the slope? Well, it starts off at 0. Okay, that matches. And then it gets larger and larger negative slope. And then again, if I can kind of draw that in, well, get something like that. And actually, if you look at this mathematically, that is a parabola, a parabolic section. So what is the maximum moment in this beam? W naught L squared over 8. That's one you'll see quite a lot because we have a lot of structures, simple supported structures with uniform load. So you'll probably, as you advance into your design stuff, your instructors in those courses will just expect you to probably know that this is W L squared over 8. You may not memorize it or remember it, but you could quickly do the moment diagram and reacquaint yourself with that. So any questions on this one? All right.